Hi everybody, welcome back to Chem 140. Today we are going to finish Unit 7. Ooh, my stomach is like gurgling right now. Uncomfortably. Let me just drink some water real quick. Okay, I think I'm okay. What are we doing? We're going to finish Unit 7. We're going to talk about ions real quick, and then we're going to talk about how to calculate the atomic mass of an atom by using a formula. And then we might start Chapter 8. Probably not. I don't know. Chapter 8's real short, so we'll finish that tomorrow, and then we'll be all set for the midterm this week. So, upcoming assignments. Quiz number 3, which is Units 4, 5, and 6, is due tonight. It closes tomorrow. Make sure you get that done before the closing date. Lab worksheet number 2 is due tomorrow as well. And when we finish Unit 8 tomorrow on Tuesday, I'm going to put the quiz up for Unit 7 and 8 for you to do. It'll be due after the midterm, but there will be special conditions about it because content from that quiz is on the midterm, and we'll talk about that tomorrow. But those are the agenda items that are coming up. Yeah, that's really all I can think of. So let's go ahead and get started here. So, we've probably talked very briefly about ions, like that you can make them by changing the number of protons and electrons within an atom. Let's formally codify that into a definition here. So, for any given neutral atom, and specifically we're using the word atom here, the total charge on an atom is always 0. And what that means is that there must be the same number of protons and electrons on an atom. Now, how does this behavior coexist? So how do the protons and the electrons stay relatively close to each other so that so that the total charge stays 0. How does that happen? Well, the way that this happens is that the electrons will buzz around the nucleus with momentum in the same way that the Earth rotates around the sun. The Earth has momentum. It's trying to go in a straight line, but the gravitational attraction to the sun causes the Earth to move in a curved path, which is its orbit. Electrons are very similar to this. They follow a chaotic path, however, because not only are they attracted to multiple protons in the nucleus, they are also repelled. Oh, I don't know why I started yawning. It's because it's 2:30, isn't it? Sorry about that. Electrons are also repelled by other electrons, so instead of following like a normal path, let me go over here to try and simulate this. So if the sun and the Earth are a very simple system. There's the gravitational attraction between the two, which pulls the Earth towards the sun. And then there's the Earth's momentum, which makes it want to go in a straight line. And the end result is that we end up going in a circle, or more of an elliptical pattern. Oops, that wasn't very good. Now, for an electron flying around a nucleus, like this, for example, there's only one attraction there. That's the attraction of charge, right? So I would get a very similar sort of result, because my electron would have momentum as well. But the second that I put another electron in here, anytime these two electrons are going to get next to each other, their path is going to go like this. Oh, I don't want to be there. Oh, and you get this very chaotic pattern that more or less goes around the nucleus, but it's unpredictable. And you might remember in Chapter 6, where we described this region as the electron cloud. The electron cloud is just the region where random shit happens for electrons. They bounce around the nucleus randomly. They don't really bounce because they aren't hitting things, but they zoom around and zip about, and all the other electrons nearby on the same atom, or adjacent atoms, or whatever, anywhere nearby in space, will just cause our electrons to fly around chaotically. So now, because there are electrons on the outside, what we can do is we can change the number of electrons around a nucleus. And that's actually pretty trivial to do. So the result of that would be called an ion. An ion does not have the same number of protons as electrons. And the way that this works is because electrons are very easy to remove. Let's get rid of that for a second here. But protons are very difficult to remove because they're in the nucleus. I can either add electrons to a nucleus, or to an electron cloud, I should say, or I can remove electrons. God, I can't stop yawning. I find electrons very boring, I guess. I don't know. I can either add or remove electrons from an electron cloud. Oops, you can't see that because I didn't actually click on the screen here. I can add or remove electrons to or from the electron cloud to create an ion. As long as I don't have the same number of electrons and protons, I would have an ion. Do the electrons make a full 360-degree rotation around the nucleus? So I'm not sure what you mean by that in terms of like position, or do you mean that they themselves spin on their own? Because electrons do spin, just like the Earth spins and causes the day-night cycle. Electrons do that, but they also go around the nucleus in a rather random and chaotic pattern. I would not call it like a 360-degree path, because their path is very abrupt and essentially random, is what I would say. On the screen here are some definitions here. If you have more electrons than protons, the term that we're going to use is anion, and if you have less electrons than protons, we're going to call that a cation. I believe this is where I did the cat's head paws positive part. Now, something to note here is that if you are removing electrons, you are removing a negatively charged thing. And what that means is that the number of protons will be larger than the number of electrons, and you will have a positive result. So, for example, if I have protons and electrons, the same number of each, the charge is 0. Now let's suppose that I took away 2 electrons. Now the charge is this, because I have more protons than electrons. But you might be thinking, like, well, wait a second, I took something away. Shouldn't it be negative? And the answer is, well, no, because you are subtracting negative charges. What happens when you subtract a negative number? You get a more positive result, right? 4 minus negative 2 is 6. So if you had a charge of 4 and you removed 2 negative charges, you'd have a charge of 6. 6 being a positive charge. So be careful with that. Make sure that you, when you are doing these sorts of considerations, like, oh, I'm going to do this to my atom, I'm going to add or remove this many electrons, that you append the correct sign to it. All right. I have this, like, suspicion that we've done these slides already. Yeah, we already did this, didn't we? I don't know why my bookmark put it right there. Give me just a second here. I'm just going to look something up real quick. That's wrong. Hold on. Yeah, we did. We totally did this. Oops. Okay. Yeah, I'm sorry. My slide bookmarker gave me the wrong thing. So we've already done all this. So you can go review the previous lecture. I'm just wasting time. Let's go on to this section. That's okay. Fortunately, I have plenty of time to waste because we are pretty much caught up on content here. So that's good. Okay, I apologize. I didn't realize that we had already done this. All right. Instead of talking about electrons, oops, what's going on? Instead of talking about electrons, what we are going to talk about today is neutrons. Now, if you have an atom that has the same number of protons and electrons in it, it will be electrically neutral. But since neutrons have no charge, you can have as many or as few of them as you want. And what that ends up doing is changing the amount of matter that is in each atom. So I'm going to give you 3 different atoms here, and we're going to analyze the differences and similarities between them. How will the midterm exam work? It's just like a quiz, except longer, and I'll tell you more about that tomorrow. So let's write down the similarities and differences of these 3 things. So we got protons, electrons, and then neutrons. So everything here is 5 protons and 5 electrons. But if I count the number of neutrons, this is the result that I get. So what we're going to do is we're going to establish a definition here. And the definition will be this. If I am looking at different atoms, and they all have the same atomic number, the same Z, but they have different mass numbers, different A, then the atoms that I'm looking at are going to be considered what are known as isotopes. An isotope is simply just an atom of a given element with a different number of neutrons relative to another atom of that same element. So these are isotopes, specifically isotopes of boron. So there's our definition again. Isotopes have the same number of protons but different numbers of neutrons. And so same Z, different A. How many different isotopes are there for a given element? It depends on the element. Very few atoms have one stable isotope. Most have 2 or 3, but some, I think tin, has up to 10. That's not why it's called that. But there are varying numbers of isotopes that you have to look up on a table called the table of nuclides. And that's beyond the scope of this class, so we're not really going to talk about it too much. But the short version is that many isotopes are naturally occurring, which means that if you were to dig around in the earth and mine up stuff, you would eventually find them. And the reason that you'd be able to find these isotopes is because they essentially last forever. That little squiggly line means approximately. Nothing really lasts forever. In 10 to the 16 years, all matter will have disintegrated into just random particles or whatever. That's the heat death of the universe. You could look that up if you'd like to know. Everything is going to fall apart eventually, but fortunately we aren't even like 1% of the way there yet, so don't worry. Most matter on Earth essentially lasts forever. So like the iron that's in the ground, or the silicon at the beach, or the oxygen in the air that you breathe, those are isotopes of those elements that last forever. Now, it is possible to create a synthetic isotope that does not last forever. So these synthetic isotopes do not last necessarily for very long. That is because they have this property to them. Synthetic isotopes are radioactive. They did exist at some point, but they radiated away, and now we don't observe them anymore. For instance, if you go digging around in the earth, you will never find any technetium. There is no technetium in the earth's soil. And the reason for this is because it is too radioactive. Its half-life is very short. It's about an hour or so. Which is kind of weird because technetium is just element number 43, I believe. Yeah. It's right under manganese. Manganese, totally stable. Rhenium, totally stable. Technetium, none at all. And I actually have no idea why that is. It's just that there's no combination of 43 protons and neutrons, any number of neutrons, that leads to a stable isotope. And technetium just doesn't exist on Earth. The only way to make technetium, because otherwise we'd have this blank on the periodic table for element number 43, is to synthesize it in the laboratory, which you can, and then we use it for things like medical imaging and stuff like that. So that's the difference between those definitions there, natural versus synthetic. For our purposes, the synthetic isotopes are interesting, but are not going to be relevant to today's discussion. We'll talk about synthetic isotopes and the radioactive particles they emit in Chem 161 a little bit. But for today's focus, we're going to stick with the naturally occurring isotopes because these are going to be the ones that if I go dig up a sample of whatever element on Earth, we're going to want to use to calculate the average mass or the atomic weight of the atoms. Now, the notation for naming isotopes is very simple. What you end up doing is you say the element name and then you put a hyphen and then the mass number after it. So carbon-12 is carbon with mass number 12, or 6 protons and 6 neutrons. Carbon-14 would be 6 protons and 8 neutrons for a mass number of 14. Now, if you want to do this for this example here, I have 12 protons and 13 neutrons. What would I call this? And you can write this in the chat if you'd like to. But first you got to look up what element has 12 protons. So that's this. And then I need to figure out the mass number, which is these two added together. And so an atom with 12 protons and 13 neutrons would be called magnesium-25. So now you know how to name elements based on isotopes. And you've probably heard all of this before. I don't know how many people were alive when Fukushima, the nuclear reactor in Japan, had a meltdown due to a tsunami and earthquake. When that happened, there was a large amount of radioactive iodine that was dissolved into the water, and so that eventually came to America, and what we had to end up doing for those of us who lived over here on this coast was take iodine supplements, because the iodine isotope that was released, iodine I think it's 131 or 125, I don't know, let me look that up real quick. Yeah, iodine 131. And iodine 131 is quite reactive. It has a half-life of 8 days, which means that if I gave you a gram of iodine 131, after 8 days, half of it would have decayed into something else. And so this is generally used, this notation, when we're talking about radioactive isotopes. Now let's do this example. How many neutrons are present in an atom of cerium-139? Well, you got to go to the periodic table, and you got to look up cerium. I'll give you a hint. It's near the bottom. And you got to find out how many protons it has. And finally, if you just subtract the mass number minus the atomic number, you get the number of neutrons. And so that would be 81. All right. There is another term similar to isotopes. These are called isobars. Isobars are atoms that have the same mass but have different atomic numbers. In other words, isobars weigh roughly the same thing, but are chemically different. For example, if you had these two atoms, they both weigh 15. So they are isobars. The intent here is that isobars are physically indistinguishable. You can't tell them apart by their weight. But they are chemically distinguishable because they are different atoms. You could do chemical reactions that work on carbon but don't work on nitrogen to discern them. With isotopes, you can't do chemical reactions because all the carbon isotopes all react like carbon. But you can separate them by weighing them or by centrifuging them or something. All right. So for the example on the screen here, I want you to tell me if these atoms are isotopes, isobars, or not, or just unique. And the way that I want you to do that is to just, we'll type it in the chat here for one. So let me number these. Where I have printed X and Y are the actual symbols for whatever these are. So for instance, if the atomic number of this one is 12 right here, then this X should not just be the letter X. It should be magnesium because that's the 12th element. X and Y may be the same symbol or they may be different, so just keep that in mind. I want you to tell me isotope, isobar, or unique in the chat. I'll give you about 3 minutes to consider it. We'll see you in a bit. One more minute, we'll go over the answers. All right, so let's go over the answers together. So first, let's look to see, we'll find what's the same. So here these are the same. So same A, different Z. So these would be isobars. And if I wanted to be specific, I could fill in their identity here. What comes after magnesium? Aluminum. I should have known that. There you go. And you can see that they're chemically distinct. They're different elements. Down here, I have the same Z, but different A. So these are isotopes. Specifically, they are phosphorus isotopes. That weigh different amounts. And then these, nothing really matches, so these are unique. So 25 is, I think, manganese, yeah. I don't have these memorized, I just have picked them up over a long time. 26 is definitely iron, that one I memorized. Not worth memorizing the periodic table, just look at it. There you go. So there's nothing in common about those two. They don't weigh the same thing, they aren't the same element, they're just unique. Okay, cool. Alright, so now that we've defined all of these things... Oh, I have more practice problems for you to try. Yeah, go ahead and do these, because we have time. So, I want you to write the isotopic notation symbol, just like I did over here, based on these descriptions, and I want you to tell me if the members of each pair are isotopes, isobars, or unique. So, we'll number these again, 1, 2, 3. And then we'll go over the answers, and then we'll keep going. So, see you in a bit. All right, one more minute. We'll go over the new set of answers here. All right, let's go over the solution here. So for number 1, I have atom X, which is 3 protons. So we'll call this 1. 3 protons and 5 neutrons. So that looked like this. The third element is lithium. And then atom 4 is 4 protons and 4 neutrons, so total of 8. And that would be this. That's not what that is at all. My heart said beryllium, but my body said bromine. I don't know. There we go. Those have the same mass number, so these would be isobars. All right, number 2, a carbon atom with 7 neutrons. That looks like that. And a nitrogen atom with 7 neutrons would be this. So these are unique. Nothing matches about them. Different masses and different identities. And then finally, we got sodium 23 and sodium 24. Those are very obviously isotopes of sodium, because they are the same element, but they have a different mass. All right, cool. So now what we're going to do is we're going to use this information to try and do some calculations. Because if you are in the business of collecting these elements, for example, maybe you need to get aluminum because you're going to manufacture with it. Knowing what isotopes are available may be relevant to what your career requires you to do. Sorry, I'm just deleting spam bots. Like, for example, maybe only one isotope of aluminum is preferred, and it's the lightest one because you don't want your cans to be slightly heavier, for instance. And that could matter if you're using a lot of aluminum. So you really just want the lower abundant or the lower mass aluminum for whatever purpose it is that you do. I don't think that that would practically be important, but I suppose that it could to some degree. What we're going to need to do first is we're going to need to discover which isotopes naturally occur and their abundance in the environment. So in this on the screen here, what we've got here for carbon 12, carbon 13, carbon 14, carbon 15. What it turns out, so this is like 99.0% abundant. This is like almost 1% abundant. There's like trace amounts of carbon 14, and there's like almost no carbon 15 at all. How did I get these numbers? And the answer is that I looked them up. So I have those facts on the screen for you, but what I'm going to show you is a Wikipedia page. So Isotopes of Carbon. So if you look these up on Wikipedia, or really any other website that has isotopic information on it, you get something that looks like this. Yeah, I don't know how much bigger I can make this, but that's okay. There we go. So what this is a list of all the different isotopes of carbon that have been observed. For example, a carbon atom with 6 protons but only 2 neutrons was observed, and its half-life was 3.5 zettaseconds, which is like times 10 to the minus 15 seconds or so, or 18 seconds. So barely any time at all. Like, it's gone. Carbon 9 managed to last for 126 milliseconds. Carbon 10 lasts for 19 seconds. Carbon 11 lasts 20 minutes. And then carbon 12 is basically stable forever. So you could see that these get exponentially less stable the further away you go from whatever the stable midpoint is. Now, only stable elements can be observed as abundant in the environment. And so that's what this column is for, normal proportion. So this is saying out of 100% carbon, 99.84% of it is carbon-12. And then out of 100%, 0.96% is carbon-13. And then that there is essentially just barely any carbon-14 at all, and then nothing else is even detected. And so this is just all experimental data. And that experimental data is collected by putting these atoms in like a particle collider and trying to create them and or destroy them and then see what happens. So you can type this in for any element. If I go up to the taskbar up here and I replace the word carbon with, you can't see it because it's off the screen there, but I can replace that with nitrogen, and I can look up any element that I want to. Other things that are on here that are important, though. Besides an abundance, every isotope has a mass. For example, carbon-12 is exactly 12. We've defined it as such. Carbon-13 weighs a little bit more than 13. Here's its mass to like 12 sig figs. All atoms will have an isotopic mass, so we can get these masses by mass spectrometer, which is basically a fancy catapult that we launch at a detector through a magnetic field, and it determines the mass of things very, very effectively. We're not going to talk about half-life just yet. We'll do that in like 3 quarters or so. But so we're going to take the percent abundance, and we're going to use that for a calculation. So that's really the only thing that I care about on this slide, is that percent abundance is what percentage of atoms that are that isotope for a given element. Atoms with high percentage abundances have the longest half-lives. But if I have 2 atoms or 2 isotopes that are stable, the percent abundance for those 2 isotopes really is just a matter of how the universe rolled the dice that day. So, for instance, carbon is 98.89% abundant and about 1% of carbon-13. 98.89% abundant carbon-12, I mean. Whereas with bromine, it's roughly 50-50, bromine 79 and bromine 81. So there's no rhyme or reason to why these abundances are how they are. It's just what we have observed. Specifically, what we have observed on Earth, I should say. There is a chance that other places in the universe could have different isotopic abundances, so their periodic tables would be different than ours because we're going to use these abundances to calculate atomic masses in just a second. Now, on the screen is the mass of an atom. That mass is really obnoxious to use because it's so tiny. It's just looking at it makes me yawn. That number is obnoxious. So what we're going to do is we're going to create a new unit. This is called the atomic mass unit. And the atomic mass unit says, okay, this is just going to be 12. We're going to call that 12. Likewise, if I do some multiplication or division, here's the mass of a proton in grams. We're going to call that roughly 1. Here's the mass of a neutron, only slightly more. We're going to call that also roughly 1. And then electrons, which weigh very, very, very little, we're going to call that roughly 0. Now, if we were taking a more basic chemistry class, such as allied health chemistry, what I would do is I would say, okay, the mass number is roughly the mass of the atom in AMU. So something that was carbon-14, for example, would have a mass of roughly 14 AMU. But because we're scientists and we're actually going to analyze this stuff in more detail and to a higher degree of precision, we're going to concern ourselves with those decimal places over here. So the 727 and this 866 here. That's going to come back later on once we're figuring out the masses of stuff, which is why when I go like this here and open the window capture back up, none of these masses in this column, in the isotopic mass column, none of them land on 0 except for carbon-12, which we've defined as such. I think that that's a footnote down here, yeah. Yeah, the atomic mass unit is defined as 1/12 of the mass of a carbon-12 atom in ground state. So this is exactly 12 by definition, but everything else you could see lands on a number that is slightly different than the whole number, but it's relatively close. So carbon-16 is almost 16 AMU, right? Carbon-22 is almost 22 AMU. So that's a good first approximation for the mass of a given atom, is you just look at its mass number, and that's its mass in AMU. But if we want to be more specific, we can look up those numbers, and we're going to want to do that so we can get more sig figs in the calculations that we're going to do in just a second. And by just a second, I mean we're going to do that after the break here, because I think, yeah, we're pretty much almost done with the section other than doing the actual calculation. So if I define mass of carbon-12 to be exactly 12, then what I'm going to do is I'm going to use this device called a mass spectrometer. And what the mass spectrometer does is it says, okay, here's my sample. I'm going to feed this into an ionizer. So now my sample has a charge on it. And then I'm going to feed this through a magnet. And what a magnet does is it has a north and south pole to it, which causes a charged... I wrote plus and minus. What I should have written is north and south. Let me fix that real quick. Oops, that's the highlighter. What this does is that when you pass a charged particle through a magnetic field, you create a current, and the current causes the charged particle to deflect in some way. So it might go like this, for example, by going through the magnetic field. And so then what we do is we just set up a detector here. And so we can then tune the magnet to be at specific masses. So for example, since we've defined carbon-12 as exactly 12, I could set the tuner to some frequency or of magnetic field and say, okay, whenever I detect that I'm hitting the target with my carbon-12, that's the magnetic frequency for 12. And then I can just magnify and amplify the field relative to that. So up here, I have learned that playing with the magnetic field, that boron-10 has a mass that is this proportion of carbon-12. So I had to turn the tuner down so that it would detect a mass 0.83442 times the mass of carbon-12. Which means that the mass of boron-10 would be this. So this is just where the numbers come from. This is sort of a curiosity. You're not going to be tested on this. You're not going to do mass spec in this class. We'll do a little bit of it in 161. And if we're doing labs on the campus, we own mass spectrometers. I just don't think that we use them for anything in our program. They do at Edmonds. I know that, because I've seen them. But their curriculum is a little bit different. We have different instruments than they do. So, all right. So that's the theory behind how we can get these masses for individual atoms. And then what we can do is we're going to weigh every possible isotope that exists naturally, that is naturally occurring. We're going to find out what their percentages are, and then we're going to determine the weighted average. And when we come back from the break here, we're going to discuss what a weighted average is and what it actually means to take an average in terms of math and stuff. So we'll deal with that after our short break here. Let me put the timer on the screen here. I'll get the music going back up for Cadence of Hyrule, which is a really good Zelda rhythm game, if you're into that sort of thing. That didn't work. Why didn't that work? Oh, weird. Oh, it's because I had minimized. Wow, I cannot talk at all. I had it minimized. There we go. Okay. All right, so take a 10-minute break. I'll see you in a bit. Alright, I'm back. And we're back. Welcome back, everybody. Let me just wind this down here. This isn't going to start immediately playing when it loads, is it? Okay, there we go. Sorry, when I wind down the music, I'm controlling something different, but the music keeps going until I hit a button. Sometimes it's like, it just suddenly starts playing again. Okay, so what we're going to do is we're going to learn how to calculate atomic masses, and the way that this works is that we are going to take, so the average mass, which is going to be the atomic mass that we're going to look at for an element, is going to be, so for whatever isotope 1 is, we're going to look at what percentage of it exists, so the percent of isotope 1, times the mass of isotope 1. And then we're going to do that for isotope 2. And then we're going to do that over and over and over and over and over until we've got all the isotopes. So this is the principle behind a weighted average. That is, if they all are different abundances, the average is going to be tilted more towards whatever there is more of. And so this is an interesting concept that we don't really explore much. Let's just put this on the screen so we have it here. In math classes, but it's a very important thing in science. So I'm going to do a little analysis for algebra here to show that point. How do you do the average of any number? So if I wanted to average these numbers together, I would add them all together and divide by 3, right? That's pretty straightforward. But I could rewrite this expression like this. Hopefully by drawing the number 4 correctly the first time, but... Right? And so these right here, these 1/3, these are my weights. And so when I take the average, I am taking an even weight of each of the numbers. The 6 is one of my 3 numbers, the 4 is one of my 3 numbers, and the 7 is 2. Now, if you have a small number of things, sure, you can do this average just fine. But we have a ginormous number of things, those things being atoms, right? The individual numbers of atoms are what we are weighing here, right? So if I was going to express that as an average, it'd be something like this. So it'd be like 2.4 times 10 to the 23rd of my 2.6 times 10 to the 23rd atoms times whatever the weight of the thing is, and so on and so forth, right? But that's obnoxious. We don't want to deal with that. So what we're going to do is we're going to just look at the percent abundance, which turns this part into a percentage. And so that's going to be our weight, is what percentage is it? So for example, let's look at the carbon example from the data. So what I'm going to do is I'm going to go to this page. So let's get this back up here again. Isotopes of carbon. So we'll go like this. That didn't do anything, and I don't know why. Let's just go over here, because I know it works here. For some reason, that window capture didn't work. So what we're going to do is we're going to write down the isotopes of carbon that are stable, and we're going to calculate the atomic mass from there. So I'm going to write this down in the background. So carbon 12 has a mass of exactly 12, and its percent abundance is 0.9984. Or in other words, 99.84%. And then carbon 13 has a mass of 13.003354 AMU. And its abundance is 0.0096 or 0.96%. Okay. So I have written down all of that information. We'll get rid of that, and then we'll just go back here. So I have written all that information down here. So now what we're going to do is we're going to apply the formula for the average mass. And that formula is up above in red. So here's what we're going to do. So for isotope number 1, which we're going to call carbon 12, we're going to take the percentage of it as a decimal and multiply it by the mass. And then we're going to do that for carbon 13. So that would be 0.0096 times the mass, 13.003354 AMU. And this is going to equal the average mass. Now we have to use our calculator and get the right number of sig figs each time we do each of these operations. So we do have to be considerate of that. So 0.9984 times exactly 12. I'm doing multiplication, so this should have 4 sig figs. This is infinite sig figs because it's exact. So the answer that I got was 11.9808, which I'm going to round to 4 sig figs for that operation. Then over here, I'm going to multiply a number with 2 sig figs by a number with 1, 2, 3, 4, 5, 6, 7, 8 sig figs. So my answer should have 2 sig figs. So 0.0096 times 13.003354. And I got 0.1248, which I'm going to rate as this. Did I multiply this correctly? Hold on. Nope, that's what I want. Okay, I guess. Okay, and now I'm going to add these together, rounding my result to the hundredths place. So 11.98 plus 0.12 gives me 12.10 AMU. And that's actually not as close. Did I use the wrong... That's not what I feel like it should have been. What are these notes? I should have gotten an answer that was much closer to 12.01, I feel. There are 2 numbers here, and I don't know why there are 2 numbers here. So here's my issue that I'm running into. So there are 2 numbers here, and the footnotes don't tell me anything. Yeah, that's just the decay. And this is what I'm more used to. So I'm going to just take those numbers, I think. So let me resolve the problem here by doing this. It's very scientific, right? If you get an answer that doesn't make any sense, just pick different numbers until it does. So we'll say, well, let's use the other numbers. So 0.9904, 0.0116. All right, and then let me see what I get for these results here. .9904 times 12. That looks better already. Okay, so 11.88. This is now 3 sig figs. 0.0116 times 13.003354. I get that, and then when I add these 2 numbers together, I have to round to this position. There, that's already much closer. So this would be the average mass of carbon for abundant carbon that is naturally abundant, is what I should say. Now, what we notice there is that if I go to the p-table website and I click on this and then I capture that window, which will hopefully do something this time. No, it totally doesn't do anything. Okay, so we're going to just remove this window capture. Let me put a new window capture in. Window capture 6. p-table. There we go. I don't know why it wasn't working before. We don't need this stuff on the bottom here. But you'll notice that for carbon, the mass of carbon is shown as 12.011, and we calculated that to be 12.03 using those numbers from Wikipedia. So we were pretty close, but we didn't have very many sig figs, which is kind of strange given that those are numbers from Wikipedia. If you do that for all the possible isotopes together, you end up getting that number on the screen here, 12.011, or you should, to a high degree of precision. And so that number is what we call the atomic mass. And the atomic mass is just the weighted average of all the different isotopes that are naturally abundant. So there's our formula for it. Now, important things to note is that when we're doing this with percentage, use percentage as a decimal. So if you have 70%, write your decimal is 0.70. Okay. If you don't, then you end up with an answer that's 100 times too big, and your result is really obnoxious to deal with. All right, so you saw me calculate the atomic mass of carbon. What I want you to do is, for this example, I want you to use this data on the screen to calculate the atomic mass of boron, and then I want you to compare the results to what you get for its actual atomic mass. So using the average mass formula, and I'll write that again here. So the atomic mass equals the percent of isotope 1 times the mass of isotope 1 plus the mass of, or percent of isotope 2 times the mass of isotope 2 plus dot dot dot. So I want you to do that for boron, and when you're done, type your answer in the chat to the correct number of sig figs, and then we'll go over the answer together in just a bit. All right, one more minute, we'll go over the answer. All right, let's calculate this over here. So we'll need the data. All right. This data I'm not actually getting from Wikipedia because I thought I got it from Wikipedia, but I know that it actually works out. All right, so we have all the abundance and percent data at the top there. Where is my pen? There it is. All right, so we're going to do the average mass and boron 10 is 19.9% abundant times a mass of 10.0129 plus boron 11, which is 80.1% abundant times, not 10, 11.0093. This is AMU. So let's do the first set real quick. So I get, 3 sig figs would be 1.99. And then over here, 0.801 times 11.0093. 3 sig figs for this would be 8.82. And then when I do the addition, I'm going to add to the hundredths place. And the result that I get is 10.81 AMU, which checks out with the atomic mass of boron on the periodic table. So there you go. Excellent. That's the wrong window. There we go. All right, next we're going to do a more complicated problem. And I'm going to have to do this one with you because this is not one that you can do on your own without having seen any example. All right, there are 2 naturally occurring isotopes of chlorine, chlorine 35 and chlorine 37. What is the percentage for each? Well, if I gave you the percentages and we determine the mass, we should be able to determine the percentages from the mass, right? Because that's how algebra works. If I can do it in one direction, I should be able to solve in the opposite direction. If I plug in x and solve for y, I should also be able to plug in y and solve for x, right? Okay, well, let's do that. And we're going to see that we're going to hit a problem immediately. All right, so here's how this works. So I know that the average mass, which I'm going to call the mass average, is equal to the percent isotope of chlorine 35 times the mass of chlorine 35 and the percentage added to the percentage of chlorine 37 times the mass of chlorine 37. Let's look at all the numbers that I know. So I know the average mass. That's in the periodic table. It's 35.453. I know the mass of chlorine 35, and I know the mass of chlorine 37. Those are shown. But I don't know these percentages. And so I have an issue. My formula has two unknowns in one equation, and those are impossible to solve precisely. For example, if I gave you x plus y equals 6, there's not one single solution, right? There'd be an infinite number of solutions. Because x could be 1 and y could be 5, or x could be 4 and y could be 2, or x could be 8 and y could be negative 2. All of those added together make 6, right? So how the heck do I find the two percentages that add up to give me the correct average when there's an infinite number of solutions for a problem with one equation and two variables? And the answer is, well, I have to make a new equation. I have to solve this somehow definitively. And the way that you do that is the following. What must the percentages equal when you add them together? Well, if there's only two isotopes, and one of them's going to be whatever percentage it is, and the other one's going to be whatever other percentage it is, they got to add up to 100%, right? So now I have a system of two equations with two unknowns, and I can solve this. And what I'm going to do is I'm going to solve this for you the long way, and then I'm going to show you the way that you should solve it, because this is an online class. Okay? So here we go. The first thing that I'm going to do is I'm going to assign these as variables, because this is what I'm solving for, right? So we're just going to erase these. We're going to do this. So I'm going to call the percentage of 35 x, and the percentage of 37 is y. All right. At this point, you could plug in all the numbers, and I really strongly recommend that you don't do that. Do the algebra first before you start plugging in random numbers. And so here's what's going to happen. I'm going to call this equation 1, and this is equation 2. And I'm going to solve equation 2 for y. So this is going to become this. Y equals 1 minus x. That's easy enough, right? And then every place I see y equals 1 or a y, I'm going to put in 1 minus x there. So now equation 1 will look like this. Average mass is x times the mass of 35 plus 1 minus x times the mass of 37. And now I have one equation that I can just solve for x, right? And let's do some algebra. So average mass equals, this doesn't do anything, but this would get factored in. So I would multiply both terms by that. I don't need these parentheses anymore because I'm not multiplying. I just have addition and subtraction now, yeah? But I need to get x by itself. So I need to isolate everything that has an x in it on one side, and everything that doesn't have an x on it has to go to the other side. So this needs to go to the other side. And then I could factor out x. Like that, right? This is still this. And then to get x by itself, I would just divide by this part, right? So that would become that. So if I solve that equation, I will figure out what the percentage of x is. Average mass minus the mass of chlorine-37 divided by the mass of chlorine-35 minus the mass of chlorine-37. So let's do that. So the average mass, according to the periodic table, which I've circled on the PowerPoint slide above, is 35.453 AMU. Chlorine-37 weighs 36.9659 AMU. You might look at that and go, that's a negative number, that's bad. Well, don't worry about it. We'll solve it and see what happens. Divided by 35 mass minus 37's mass. All right. Don't cancel these out. You can't do that with subtraction. We have to do the subtraction first before we can do any division. So I'm going to record these to the correct number of sig figs. These both go down to the thousandths place. These go down to the 10,000ths place when I do the subtraction vertically. So when I punch in my calculator, here's what I get. On the top, I get minus 1.513. And on the bottom, I get minus 1.997. These then cancel out. These become positive. And x is just whatever that percentage is. 1.513 divided by 1.9970. And the result that I get is 0.7576. So that means X, which was chlorine-35, is 75.76% abundant. And therefore, Y, which was chlorine-37, which was the rest of it, is 1 minus that, or 24.24% abundant. And if you're sitting there going, oh, not just no, but fuck no, I don't know how the hell that happened. That's because I'm doing algebra. Nobody's done algebra for 75 million years, right? I'm apparently the last person on Earth that does algebra. Apparently. Well, me and every other math instructor at EVCC. So I would prefer that you do it this way. In fact, if this was an in-person class, I would insist that you do it this way. But this is an online class. And that's where this comes in. This is Wolfram Alpha. Wolfram Alpha is an online calculator that is incredibly useful and incredibly powerful. And what we're going to do is we're going to just take our equations that I wrote at the very, very beginning here, which you can't see because I'm scrolling up with that in the way. I'm going to take these equations that I wrote at the beginning here, that I'm putting in a blue box, and we're just going to type them in there. But we're going to type in the numbers for the equation. So the first equation that we're going to type in is going to have this with a number in it, this with a number in it, and this with a number in it. We're going to leave x and y as they are, where x is the percentage of 35 and y is the percent of 37. So your equation is going to look something like this. So the average mass, which was 35.453, equals x times the mass of 35, which I need to find what those numbers are, actually. So that was this plus y times the mass of 37. So that's equation 1 with the numbers plugged in. And then the second equation is simply, well, x plus y equals 1. And you hit enter and it's going to solve it. And it's going to solve it real fast. Look at that. don't even have to do all the algebra, right? Like, look at this compared to the result that we just got. How did we do compared to Wolfram Alpha? Well, we did real darn good, but it took us a while to do, right? I probably spent like 10 minutes doing this equation, whereas you could just type it in Wolfram Alpha and do it in 10 seconds. So that's my suggestion to you, is if you see a problem like this on your quiz or exam, hint, you will, go to Wolfram Alpha and type in the equations there. You have to still make the equations, so you still have to be able to create these two equations. And that's kind of the chemistry of this, right? Can you turn the information in this problem into these equations? If you can, I feel like that's good enough. I've tested you on the chemistry part. I don't really give a shit about the algebra, right? This isn't a math class. Math is supposed to be a tool, and I don't want you to get stuck on the math. So make Wolfram Alpha do it. It will give you the answer. And then you can look at this. There's all sorts of other fun stuff that Wolfram Alpha can do. Like, it plotted the equations and solved for the result. I think we can enlarge this. Oh, I can't because I don't have the pro version. I'm using the cheapo version. But yeah, so here's the website for that. So this is wolframalpha.com. Super useful. Please use it for all your calculation needs. If you don't have a graphing calculator, that can do this easily. All right, so we did that problem. So now I'm going to give you the exercises here. And you can use Wolfram Alpha to solve the bottom one in the exact same way that I just did. The top problem is what we basically did earlier in the period, which is do the calculation to the correct number of sig figs, and then compare it to the mass shown on the periodic table and tell me how close you get. So I'm going to have you do these exercises for now. In about 5 or 6 minutes, I will do the Wolfram Alpha calculations for both of them so that you get the answer. Don't worry about sig figs for these. Really, I'm just trying to get you to get the percent to enough digits that you can show that you've done it correctly. Okay? So go ahead and try these, and we'll go over the answers in about 5 or 6 minutes. All right, one more minute. We'll go over the answers, and then we'll call it a day. All right, so let's very quickly do the top problem, and then we'll type the bottom problem into Wolfram Alpha. Forgot the name for a second. So, all right, so I'm always losing the stylus because I never put it in the same place. Okay, so the average mass for the silicon will be 92.223% abundance, 27.9769 plus, let's see here, 46858 times 28.9765 plus 30921% abundance times 29.9738. All right, so with sig figs, that will give us 0.92223, 27.9769. So that's 5 sig figs. So I got 25.801. And then 0.046858 times 28.9765. That's 5 sig figs also. And then the last one, that's also 5 sig figs, so I should, let's see, 92682. I'm going to add all those together, and they should go to the thousands place, so 3 decimals in. And so when I did all of these to get added together, I got 28.086 AMU. And how does that compare to our periodic table for silicon? I do still have that. Here we go. Click on silicon right there, and let's see what we got. So window capture is that. Boop. Look at that. So we got 28.086 using sig figs. The correct answer is 28.085. That is real close and real good. All right, so let's do the next one. We're going to write out the equation so that we can put it into Wolfram Alpha. So we have the average mass is the percent of isotope 70 times its mass plus the percent of isotope 73 times its mass. And so with numbers, that would be, so 71.225, oh, 255, sorry. Equals percent 70, we'll call that X, times the mass of 70. Plus the percent of 73 times the mass of 73. And then, of course, this must be true. So now we'll go to Wolfram Alpha. input all of that into the equation editor. So 71255 equals x times 69.938 plus y times 73.014 semicolon x plus y equals 1. And you should have got 57% and 42% for x and y. So if we go back over to here, then since x was for 70, so 70x is, according to Wolfram Alpha, and I can't read it because it's too tiny in that display. And then that one was 42.82. And we'll just do 4 sig figs because I told you not to worry about sig figs for that. There you go. I believe that is everything from this chapter. So when I hit this button, it should do the hooray. So we'll put the little volume notification. There we go. So yay. All right. Hooray. That's it for chapter 7. We will do Unit 8 tomorrow, which is very short. It's just about the periodic table. We're going to talk about groups and columns and stuff. And yeah, that's really all I got. So I do want to thank everyone for coming out to the lecture. Make sure that you get your quiz for Units 4, 5, 6. That is due tonight. It closes tomorrow. Make sure to get that by the deadline. And then lab worksheet number 2, which is the density assignment, is due tomorrow and closes Wednesday. We'll talk about the Unit 7 and 8 quiz tomorrow, as well as the exam. Until then, start your preparations for the exam on Friday. And I'll see you tomorrow. Have a wonderful rest of your evening, and take care.